morning. Today's topic is numerical differential protection of transform. In the last lecture, we have discussed about the numerical overcurrent protection of transformers. We have seen the important things which we need to consider. We have seen that we need to consider the pickup currents, the characteristics of the relay, the time relay setting, the characteristics of the relay, whether there is any communication, which type of communication protocol we want to use, and coordination with other existing relays. All these things we need to consider before we design a numerical overcurrent protection for transformers. And then we have tried to how to implement the numerical overcurrent relay, the procedure, and we have also seen we have developed a flowchart for the numerical overcurrent relay algorithm. And also finally we have gone through a Siemens developed overcurrent relay. We have seen what the LEDs display when they get a display, and we have seen the functions which will be provided by this Siemens overcurrent relay. In today's class, we will discuss about numerical differential protection. So I hope that by the end of this lecture, you will be able to describe the numerical differential protection for transformers. So I'll start with the basic introduction, why differential protection, and next we will move on to the block diagram, and then the dual slope characteristics, which is widely followed now, and then we will move on to steps involved in numerical differential protection. And finally, we will have a look at Siemens differential protection relay number 87. So coming to the introduction, you know that your differential protective relay, we have seen in unit number 3 also, differential relay is generally employed for internal faults. So differential protective relay is generally employed for internal faults. So it functions on a percentage or phase angle or any other quantitative differences of two currents. It's not only about two currents, it can work on quantitative difference on two voltages also. You can have a current differential relay or a voltage differential relay also. The differential relay is employed protecting your devices against any internal faults. It can be a transformer, it can be a bus bar, it can be a generator. Any of the devices can be employed for due protection. So, how it is basically implemented is, let us suppose if you do have a device, let us suppose this is the incoming current and this is the outgoing current. So normally, the current which is passing through here, under normal cases, I1 will be equal to your I2. If at all if there is any fault which is happening in between here, internal fault, so then automatically the current will be flowing in this fashion and the current will be flowing in this fashion. Then in that case, I1 is not equal to I2 in case of internal faults. So you will be always comparing I1 and I2. If I1 is not equal to I2, then automatically you will give a trip signal. So this is how your differential relay works. So in ideal case, the difference between I1 minus I2 must be 0 or it must be less than your pickup value of the current. If it is greater than 0 or your pickup value, then it means that there is an internal problem with your device. So in that case, relay will be giving a trip signal. So how this is achieved? This you will be employing CTs here and the currents will be measured here. So differential relays provide sensitivity by providing a zone of protection with a circuit of interconnected CTs. These are the interconnected CTs on either sides of your device. Now, the CTs having the same ratio, most of the times same ratio, but in case of a transformer, the CT ratios may not be the same. CTs having the same ratio are installed in all the connections to the component. In case of example of transformer, it will be a little bit different, that I will explain again. And the secondary of CTs are connected in parallel to the relay in order to measure the difference of currents, I1 and I2. Now, as long as the current flows through the protected component, is unchanged in both maximum and phase, the relay does not pick up. So this is one current, this is another current. This is I1 and this is your I2. Okay, so this is your I1 and this is your I2. So what will the current which will be flowing in this one? It will be I1 in this, because I2 will be flowing in this fashion, I1 will be flowing in this fashion. Okay, so as long as your is equal to 0 or less than IPU, your relay will not pick up. Such a condition would occur for a short circuit fault outside the zone. Even if there is any outside fault also, external fault also, there won't be any change in difference of the currents I1 and I2. But if there is any internal faults, then automatically what happens? Here I1 minus I2 may be greater than 0 or maybe greater than your pickup value. Then automatically what happens is your relay starts working. So this is the block diagram of your numerical protection. See here, this is your source, whatever you call it as. So this is your primary side. So let us suppose this is your device. In this case, I am using a transformer. This is your primary side CT. This is your secondary side CT. So this is the voltage which is across your CTs, and this is your currents IP, and this is your IS on the secondary side of your transformer. Now both can be transformed into your voltage. So if you want voltage signals, you can take voltage signals. If you want current signals, you can take current signals. And these things will be fed here. In case of a numerical relay, normally what happens in case of a normal relay, the IP minus IS will be tested, or VP minus VS, or V1 minus V2 will be tested. If it is greater than your pickup values, then automatically what happens is you will be giving an alarm, provided the same things will happen again and again. See, this is just like your, you assume that it is a current, so it is just like delta I is greater than your IP. If you carefully see in the last slide, you have already seen this is the fundamental concept of your overcurrent relay. So it is just like your overcurrent relay being modified in order to identify the diagnosis system for internal faults. So the same thing, what you are supposed to do, you are supposed to again have your pickup value, the time delay setting, your relay characteristics, etc., etc. Apart from this, there will be a constant which we call it as a percentage bias. So that is another thing which we will be discussing in the class. It is just like I1 minus I2, this is your delta I, is greater than your K into I1 plus I2 by 2. Okay, this is your differential current, this is your bias current. So this is your percentage bias, which we call it as. Okay, so all these things, they will be provided to your numerical relay, and based upon that, it will compare these two signals. One is I1 minus I2, the other one is I1 plus I2 by 2, and based upon that, it will wait for some time based upon your time delay setting, and then it provides you a trip signal. So all this algorithm which you need to do, you are supposed to develop as a programmer. Okay, so this is the characteristics. So this is your bias current, which I told you, and this is your differential currents. Okay, so if your differential current is greater than your bias current, then this is your trip zone. If it is less than this one, then automatically it will be restrained. So you won't be getting any trip signal. Okay, the minimum value is going to be an IP, pickup value of the currents. So now, how to develop an algorithm? See here. First of all, what are the things which you are supposed to do? You read the percentage bias, the minimum pickup value, and also other things which you do have, just like your TDS, time delay setting, characteristics of the relay, etc. All these things you are supposed to read. And see here, you are supposed to detect two currents. One is from the primary side, the other one is the secondary side. So the primary side, you pick up the samples and estimate the phasor using any of your FFT techniques which you have seen in the last class. And then on the secondary side also read the samples and then estimate it. Now, if you do have this IP and IS both, you need to do two calculations. One is the spill current, IP minus IS. We have seen this in the case of the first part, differential protection. So the same thing here also. It is IP minus IS is one thing. The other thing is bias current. What is it? IP plus IS by 2. Okay. So now if this spill current, what I call this one as spill, I call this one as a circulating current. If it is greater than your B, this is your percentage biasing, plus your pickup value. Then automatically what your relay must give a trip signal. Otherwise it must wait. Okay. Here also you can include your time delay setting. You can wait for some time. Even after the time also, again you need to check. If it is still there, then you are supposed to trip your signal. Otherwise you can get back to your samples collection. Okay. So for this one you need to develop flowchart, and that is to be practiced in the class. That will be your homework. Okay. Now coming to, as already I said, I have shown you that this is the characteristic of your differential relay, which means that this is your differential current, or we call it as, you can call it as spill current also, which is equal to your I1 minus I2. The other one is your bias current. We call that one as circulating current also. It is I1 plus I2, right? So there will be a minimum pickup value, and there will be a bias setting also. So the slope between these two, it will be like this. Okay. Based upon this K value, this characteristic will be changed. Okay. So now I have taken this for some K value. Now if your current is greater than the operating points, you will note down what is this value and we will note down this value. If the operating point is lying in this region, then automatically the relay will give a trip signal. If it is lying in this region, then it will restrain from giving a signal. This is how it works. This one is called as a slope. Normally we are used to have a single slope characteristics, but in modern days we are employing dual slope characteristics. This is what you should remember. So why dual slope characteristics? See, this is your minimum pickup value, and after that this is one thing which we have been following from so many days. But now a second slope characteristic is also being operated now. So which means that these are your characteristics now. Slope 1 and slope 2. Why slope 2 has been introduced? See, ER transformers suffer from different problems. Okay. Now you do have three characteristics. One is a constant characteristic of IPU. The next one is a single slope. The other one is a second slope, number 2. So what is the advantage of having this many number of slopes? See, this has been mentioned here clearly. Why you should have a minimum value? Because most of the times what happens is there will be a sudden inrush currents. There can be errors in CT ratios. There can be unequal load lengths. So for that case, you need to maintain some minimum value of pickup value that is required. The next thing is slope. Slope 1, as already we have discussed in unit number 3. Why we will maintain this? We don't take this one. Instead, we will take K into I1 plus I2 by 2. Why it is being mentioned? This has been included in order to include your CT ratio mismatch. Most of the times your CT ratio may not be the same. So to include that one, we have included this particular thing, and we call it as percentage bias. So you can adjust the tap changes. You can have non-identical CTs also. For all that one, this is the compensation. Slope 1 is the compensation for that. And you have seen that there is a double slope also. Why it is being done is nothing but, as already we have seen in unit number 3, again, your CTs may be experiencing a saturation. So to avoid that thing, what we are doing, normally we will be placing a high impedance or high resistance in series with your overcurrent relay or your detection relay. So for that one, I am including an additional slope. We call it as a second slope, and this helps us to avoid the errors due to external fault with CT saturation. So that's why your characteristics have become, rather than, so this is to protect your system or to get perfect results in case of heavy inrush currents or errors in CTs. The second one helps you to give you good results even there is a difference in tap change ratios and even if the CTs are non-identical. And the second slope will help you to give good results in case of CT saturation also. So this is the case. Now If your operating point lies in this region, then you will be giving a trip signal. This is your operating region and this is your restaining region. Okay. So I hope that now you have understood why we are going with dual slope characteristics. The next one comes here. As already I said, these are the things, but